Okay, let's unpack this. Imagine trying to replicate the exact function of a human organ using, of all things, the sperm of a trout.
Right. I mean, it sounds like a completely bizarre science fiction plot.
It really does. But that specific biological hack actually became a medical standard that kept millions of people alive.
Mm.
Today, we are diving into insulin.
And we really need to set the stage here because we aren't just defining the hormone, the standard 51 amino acid peptide in biology textbook.
Exactly. For you listening, our mission for this deep dive is to explore a century-long engineering challenge. Scientists spent 100 years trying to artificially mimic the human pancreas, turning this single molecule into, well, a really complex toolkit of highly manipulated drugs.
Right, because for the millions of people who use it, insulin functions as a manually operated life support system. So when we talk about insulin as a pharmaceutical, we classify it based entirely on its pharmacokinetic profile, meaning how it moves through your body.
Okay, so what are the nuts and bolts of that profile?
We measure three strict variables. First is onset, which is how quickly your blood glucose starts falling after an injection. Then there's peak, the moment of maximum effect.
Yeah.
And finally, duration, which is just how long the drug lasts before it completely wears off.
Onset, peak, and duration. So those three variables basically dictate every single thing we're going to talk about today.
They absolutely do.
But before we get into like the modern genetic engineering and all that, we really have to understand the biological problem that forced us to invent different versions of this hormone in the first place.
Yeah, and it all goes back to the natural rhythm of a healthy pancreas.
Right, because the pancreas doesn't just dump one giant dose of insulin per day, does it?
No, not at all. In a body without diabetes, it maintains a continuous, extremely low-level trickle around the clock. We call this basal insulin. It works in the background to keep your blood sugar stable while you sleep or, when your liver naturally releases stored glucose.
I always like to think of it like a dual-setting faucet in a kitchen sink.
Oh, that's a good analogy.
Yeah, so the healthy pancreas leaves the faucet on a slow, steady drip all day long, just to keep the pipes from freezing. That is your basal trickle. But then you eat a meal and suddenly you have this massive load of dishes to wash.
Right, you need more power.
Exactly. You hit a button and get a high-pressure blast of water to clear the sink. That high-pressure blast is the bolus spike, the immediate surge of insulin the pancreas releases to move a flood of food-derived glucose into your cells.
But the core problem in medicine is that a single injection of liquid from a syringe just cannot do both of those things simultaneously.
It's either the drip or the blast.
Exactly. And in the early 1920s, when insulin was first discovered, scientists didn't have a dual-setting faucet. I mean, they barely had a bucket, and the bottom was leaking.
Let's ground this in that 1920s reality for a second. So it's the University of Toronto, 1921. You've got this team, Frederick Banting, medical student Charles Best, biochemist James Collip, and physiology professor John McLeod. They discover insulin, they create this extract from animal pancreases, and by January 1922, they inject their first human patient, this 14-year-old boy named Leonard Thompson.
That first attempt was incredibly crude.
Yeah, didn't it cause some major issues?
It did. It barely lowered his blood sugar, and it actually caused a sterile abscess at the injection site.
Wait, what exactly is a sterile abscess?
So it happens when the immune system detects foreign impurities. In this case, other random animal proteins were mixed in with the crude insulin. The immune system attacks the area, creating a painful pocket of inflamed dead tissue, but without any actual bacterial infection.
Oh, wow, that sounds awful.
It was. It took James Collip 12 more days to purify the extract enough for a second injection to actually work properly.
And the success of that purified injection triggered one of the most famous feuds in medical history, right?
Oh, definitely. The Nobel Prize drama.
Yeah. The 1923 Nobel Prize is awarded for the discovery, but the committee only recognizes Banting and McLeod. Banting is furious that Best was left out, so he publicly gives Best half his prize money.
And then McLeod immediately turns around and splits his half with Collip.
It's just intense drama.
Yeah.
But beneath all the Nobel glory and the infighting, the patients themselves were facing a severe practical crisis.
Right, because while the crude extract saved lives, its duration was incredibly short. I mean, the body processed it in just a few hours.
Meaning the faucet shuts off completely. That basal background drip just disappears.
Exactly. So to survive, patients in the 1920s and 30s had to inject themselves repeatedly throughout the day and night, and they were using these thick, reusable glass syringes.
Oof, that sounds painful.
Painful, expensive, and just totally unsustainable long term. So the biological target shifted. Scientists realized they didn't need a more powerful hormone. They needed a mechanism to deliberately trap the hormone they already had under the skin.
To basically force the body to absorb it slowly over a full day.
Right.
Which brings us back to the trout sperm.
Yes, the famous 1936 breakthrough.
Here's where it gets really interesting. A Danish physiologist named Hans Christian Hagedorn actually figured out how to create this slow-release trap. He added a substance called protamine to the insulin.
And protamine is a highly alkaline protein found in the sperm of certain fish, like salmon and trout.
I just marvel at the bizarre ingenuity of that. Mixing fish sperm protein with a hormone to delay its absorption in humans, how does that even work?
It's actually entirely based on electrical charge. Insulin molecules naturally have a negative charge, and protamine has a positive charge. So when Hagedorn mixed them together, the opposite charge is attracted.
Like magnets.
Exactly. It bound the molecules together into tightly packed crystals.
So when a patient injects this crystal mixture into the fluid under their skin, the insulin can't just immediately enter the bloodstream.
Right, it's trapped. The body's tissue enzymes have to slowly chip away at the protamine, basically digesting the fish protein bit by bit.
And as the protamine breaks down, the trapped insulin is gradually released into the blood.
It was a brilliant manipulation of biochemistry. By 1946, Novo scientists stabilized this mixture into neutral protamine Hagedorn, or NPH insulin, as we know it today.
And NPH stretched that duration to roughly a day, right?
Yeah, it remained the global standard for basal insulin for decades. And then in the 1950s, scientists also developed the Lente series, which used zinc instead of protamine to do a similar thing.
Zinc causes the insulin to clump up, right?
Yes, into geometric shapes called hexamers, which take a long time to dissolve in the tissue.
So for like half a century, the main way we created long-acting insulin was literally throwing physical obstacles like fish protein or zinc at the molecule to slow it down.
Exactly. But in the 1980s, the entire paradigm shifted. We moved from chemical mixing to genetic engineering.
Right. Eli Lilly releases Humulin in 1982.
Which was huge. It was the very first genetically engineered drug approved by the FDA.
Because before this, they were harvesting pancreases from millions of slaughtered cows and pigs.
Yeah, millions of them. But with recombinant DNA technology, scientists could take the human gene responsible for producing insulin and insert it into the DNA of bacteria or yeast.
Turning microbes into microscopic factories.
Exactly, churning out pure human insulin. And once they realized they could dictate the genetic blueprints, they stopped just mixing obstacles into the vial.
By the 1990s, they were literally redesigning the amino acid sequence of the insulin molecule itself.
Yes, and this genetic redesign gave birth to the analog insulins. This is what allowed us to build the highly specific, modern arsenal of treatments we use today.
So let's break down that modern arsenal for the listeners. We've got the fast-acting bolus insulins and the slow-acting basal insulins.
Let's start with the fast-acting squad.
Okay, so rapid-acting analogs like lispro, brand name Humalog, hit the market in 1996. And the onset of lispro is incredibly fast, right? Like 10 to 15 minutes.
It is. And to understand how they achieved that speed, you have to look at the physical bottleneck they had to eliminate from older insulin.
Right, the hexamer thing.
Yes. Regular human insulin naturally clumps together into those 6-part groups, the hexamers, when it's just sitting in a vial.
And when you inject those clumps into the body, they're too bulky to enter the capillaries.
Exactly. They have to physically break apart into single molecules, monomers, before they can cross into the bloodstream. That breaking apart process takes time.
It's a major bottleneck.
So scientists looked at the molecular chain and found the exact spot where these molecules were linking together.
And they did a brilliant molecular tweak.
They did. By swapping the positions of just 2 amino acids, proline and lysine, they physically changed the shape of the molecule's edge.
It's like taking a puzzle piece and just filing off the connecting tab.
That's a perfect way to describe it. The molecules simply couldn't snap together into hexamers anymore.
So they just stay as single molecules in the vial, and they absorb almost instantly when you inject them.
Which was a massive improvement over the older, short-acting regular insulin. Because that older one still had the hexamer bottleneck, it took 30 to 60 minutes to start working.
I mean, think about the practical reality of that. With regular insulin, a patient had to inject sit at the dinner table, and wait exactly half an hour to take their first bite of food.
Right, and if they miscalculated or the food was delayed.
The insulin would peak while their stomach was empty, causing a dangerous crash.
But the rapid-acting analogs let patients dose right when the meal begins, which safely matches the body's natural bolus response.
Okay, so genetic engineering perfected the rapid mealtime spike. But they also applied these structural tweaks to the other side of the equation, right?
Yes, creating the perfect, flat, 24-hour basal drip.
Let's talk about those workhorses.
Sure.
We mentioned NPH earlier, the one with the protamine. One highly specific signature of NPH is that it's cloudy in the vial.
Right, and that milky appearance is the literal suspension of protamine and insulin crystals floating in the liquid.
And because it's a suspension, the crystals settle at the bottom.
So patients have to gently roll the vial or the pen to remix those crystals before drawing a dose.
Because if they don't mix it, what happens?
They might draw pure liquid one day and a concentrated clump of crystals the next, leading to completely erratic blood sugars.
That sounds super unpredictable.
It was. The ultimate goal was a clear liquid that could provide a perfectly flat 24-hour basal drip without those unpredictable peaks.
Which led to the ultra-long-acting analogs, starting with glargine brand name Lantus in 2000.
Glargine tackles the duration problem through a really clever manipulation of pH levels.
Oh, this part is fascinating.
So the insulin molecule is genetically altered so that it completely dissolves in an acidic liquid. Inside the vial, it's clear and acidic.
But the human body's tissue under the skin is pH neutral.
Exactly. So the moment glargine is injected into that neutral environment, it instantly undergoes a chemical reaction and precipitates.
It basically crystallizes inside your body.
Right under the skin. It forms this tiny microcrystal depot. And the outer layer of that depot very slowly dissolves over roughly 24 hours.
Releasing a steady trickle of insulin into the blood with almost no peak. But then scientists push the duration even further, right? With degludec brand name Tresiba, which was approved in the U.S. in 2015.
Yes, and degludec doesn't precipitate based on pH. Its genetic tweak causes the molecules to snap together into incredibly long multi-hexamer chains once injected.
Like an endless string of Lego bricks.
Right. And the body can only pull insulin molecules off the very ends of these massive chains.
Which extends its duration to over 42 hours.
Which naturally brings up a pretty big mechanical question.
Wait, I know what you're going to say. If a patient injects degludec every 24 hours, but the drug lasts 42 hours, won't those doses overlap in the tissue?
Exactly. And looking at the DEVOTE clinical trial, you might initially assume that overlapping would cause the insulin to dangerously build up.
But it doesn't.
No, the trial proved that because the release from those multi-hexamer chains is so agonizingly slow and flat, the overlap simply creates a continuous steady state.
So the practical benefit of a 42-hour duration is actually just timing flexibility for the patient.
Right. If a patient takes their dose at 8 a.m. one day, but forgets and takes it at noon the next day, the baseline is so stable they don't experience a dangerous gap in coverage.
That is incredible.
Yeah.
So having mapped out all this molecular precision from 10-minute rapid onsets to 42-hour slow burns, we really need to pivot to the high stakes of getting that timing right.
Yeah, if we connect this to the bigger picture, the stakes are literally life and death.
Let's look at the landmark Diabetes Control and Complications trial, the DCCT, which ran from 1983 to 1993. The data presents a terrifying trade-off.
It really does. The study proved that intensive therapy using multiple daily injections to strictly mimic a healthy pancreas prevented long-term microvascular damage.
It massively reduced the risk of blindness, kidney failure, and nerve damage.
But achieving that near-normal blood sugar tripled the rate of severe, immediate hypoglycemia.
Tripled it. That is the terrifying tightrope walk patients face every single day.
Right. If a patient runs their blood sugar slightly high, they quietly damage their capillaries over a decade. But if they miscalculate an insulin peak and drive their blood sugar too low, they risk a seizure, a coma, or death that very afternoon.
And despite those massive stakes, the medical system itself frequently failed to use this timing properly.
Oh, absolutely.
Like in hospitals. For decades, they stubbornly clung to something called the sliding scale approach.
Which was incredibly flawed. Instead of providing a steady, long-acting basal insulin and proactive mealtime boluses, nurses were instructed to wait until a patient's blood sugar spiked.
And then reactively administer short-acting insulin to knock it back down.
It was a reactionary roller coaster. It completely ignored the proactive pharmacokinetics of the drug.
And the 2007 Rabbit 2 trial formally proved how dangerous that hospital habit was, right?
Yes, it showed that a proactive basal bolus regimen in the hospital produced significantly better glucose control and drastically lowered complication rates compared to the reactive sliding scale.
But, misunderstanding insulin's timing has historically led to much darker outcomes than just outdated hospital protocols.
It has. In the 1920s through the 1950s, a psychiatrist named Manfred Sackel popularized this deeply disturbing practice known as insulin shock therapy.
For schizophrenia, right?
Yes. Psychiatrists deliberately injected patients suffering from schizophrenia with massive, overwhelming doses of insulin.
Because the brain relies almost exclusively on continuous glucose to function.
Right. So by flooding the body with insulin, they stripped all the glucose out of the blood, literally starving the brain of its fuel until the patient fell into a hypoglycemic coma.
And there was no real evidence base for this, right?
None. The underlying unscientific theory was that the severe biological trauma of the coma would somehow reset abnormal neural pathways.
That is horrifying. It carried a massive mortality risk and remained a mainstream psychiatric practice for decades before controlled studies finally proved it was no more effective than basic sedation.
It's a glaring example of exploiting the raw power of a drug while completely disregarding its actual physiological purpose.
And speaking of dark exploitations, there's a forensic true crime angle here, too.
Ah, yes. Because insulin's onset and peak are so strictly predictable, prosecutors have actually used its pharmacokinetics to catch poisoning murderers.
Like the nurse Charles Cullen.
Exactly. He murdered dozens of patients by secretly injecting insulin into their 5e bags.
But investigators used the drug's exact timing window to catch him.
They did. They used it as a molecular witness. If a medical examiner knows exactly which type of insulin was found in a victim's tissue, they can trace the strict duration and peak window backward.
To pinpoint the exact hour the fatal dose was administered, the biological math is just unyielding.
And that unyielding nature brings us to the everyday reality for the 8.4 million Americans using insulin today.
Right, because real-world misconceptions about how these different analogs operate carry immediate physical consequences. So let's rapid-fire bust some of these myths from our sources.
Let's do it.
Myth number 1. The 30-minute wait myth. People think if you take rapid-acting insulin, you should still wait 30 minutes before eating.
Yeah, that's dangerous. That 30-minute rule only applies to the older, short-acting regular insulin with the hexamer bottleneck we talked about.
So if you do that with a modern rapid analog,
If a patient injects an analog like lispro and waits 30 minutes, the drug will hit its peak action while the stomach is still empty.
driving blood sugar dangerously low before the food even reaches the bloodstream.
Exactly.
Okay, myth number 2. The mixing myth. Some patients assume they can draw their long-acting basal and their rapid-acting bolus into the exact same syringe to avoid taking 2 separate shots.
This is a huge misconception. While older human insulins like regular and NPH were designed to be mixed, you can never, ever mix modern long-acting analogs like glargine in a syringe with anything else.
Because it destroys the mechanism.
Completely. Remember, glargine's slow-release mechanism relies entirely on its acidic pH reacting with neutral body tissue.
Oh, right. So if you pull glargine into a syringe containing another insulin with a different pH,
You trigger that chemical reaction inside the plastic barrel of the syringe. The glargine precipitates before it ever enters the body, completely destroying its 24-hour delayed release mechanism.
wow, okay. Myth number 3. Long-acting basal insulins have absolutely no peak at night.
Well, the older MPH insulin has a very pronounced peak 4 to 12 hours after injection, making it a notorious culprit for nocturnal hypoglycemia.
But what about the modern ones?
Even modern ultra-long-acting analogs can exhibit a mild peak depending on the dose size. So while the risk is much lower than with NPH, nocturnal lows remain a physiological reality.
So we've spent this deep dive mapping out this incredible toolkit of precise, genetically tailored medicines. But what does this all mean for the patient at the pharmacy counter today?
Well, the sources highlight a stark friction point between biological engineering and everyday reality, which is the affordability crisis.
Right, because the marketplace creates a really difficult dilemma.
It does. The newer, precisely engineered analog insulins lispro, glargine, degludec are patent protected and inherently expensive.
Whereas the older, harder to time human insulins like regular and NPH are available much cheaper, sometimes even completely over the counter depending on where you live.
And this dynamic forces a brutal calculation for patients who lack robust insurance.
They basically have to weigh the genuine safety of perfectly timed analogs against the hard financial constraint of what they can actually afford.
Right, because choosing the cheaper, older insulin means actively choosing a higher risk of mismatched peaks and severe lows.
And this specific friction between cost and ideal pharmacokinetics is what recently drove major policy interventions, right? Like the recent Medicare legislation that capped out-of-pocket insulin costs at $35 a month for seniors.
Exactly. These interventions occurred precisely because the safest, most physiologically accurate versions of the drug were financially inaccessible to a large portion of the people whose lives literally depend on them.
It is just remarkable to reflect on how a single hormone, isolated in a Canadian laboratory a century ago, now demands such an intricate daily calculation of onset, peak, and duration.
It really is.
I mean, insulin demonstrates perfectly that having the correct medicine is only half the battle. Controlling the timing of that medicine is what ultimately dictates survival.
Absolutely. And I want to leave you with a final thought concerning the future of that timing, specifically regarding continuous subcutaneous insulin infusions.
Oh, you mean insulin pumps, the wearable devices that automate the delivery.
Yes. What is structurally fascinating about modern insulin pumps is that they completely abandon the dual drug approach.
Wait, what do you mean?
They do not use long-acting insulin at all. A pump is filled exclusively with rapid-acting insulin.
Wait, really? No long-acting basal at all?
None. The device relies on a computer algorithm to continuously pulse microscopic drops of that rapid insulin to artificially mimic the basal trickle, and then it delivers larger surge doses for the mealtime bolus.
Oh, wow. So after a full century of brilliant pharmaceutical chemistry, spending decades inventing complex fish protein traps and genetically engineered multi-hexamer genes just to create long-acting basal insulins.
The rise of algorithmic robotics might eventually render the entire long-acting drug category completely obsolete.
That is wild. That changes the entire trajectory of the science. Well, thank you for joining us on this deep dive. As always, keep exploring.